Hello, class. Today we are going to review an application of equilibrium called LeChatelier's principle. LeChatelier's principle states that if stress is applied to a system in equilibrium, then the system will change in order to relieve that stress. So there are several different stresses we're going to review today. One is a change in concentration, either by adding or removing reactants or adding or removing products. There's also changes in temperature, which affects systems that are endothermic and exothermic. There's also pressure changes. We know that due to our relationships from kinetic molecular theory and gas laws, that pressure and volume have an inverse relationship, which means as pressure increases, volume decreases. And therefore, that affects the number of successful collisions that could occur on a system at equilibrium. So we're going to look at how all of those changes manifest themselves and how it changes our concentrations of reactants and products. So remember that equilibrium means that the rate of the forward reaction and the reverse reaction are equal. It doesn't necessarily mean the concentrations are equal at that point in time, but the concentrations are constant and there is no net change in concentration at equilibrium. So if we introduce a stress, such as adding reactant, we've increased the total number of particles on one side of our reaction. Therefore, there are more possible collisions that can occur between reactants, and this will result in an increase in the rate of the forward reaction. More collisions, an increase in rate. And therefore, to deal with the increased rate on the forward direction, we are going to shift towards the right side to increase the amount of products that we have. So let's see this in action. We're going to increase the rate temporarily of our forward reactions. So here we have a system at equilibrium, and you can see that the reactions are still occurring, but the forward and reverse rate are equal, and so there is no net change. You can see down here H2 and I2 are staying the same in terms of concentration, and the amount of HI we have at equilibrium is staying the same in terms of concentration. So let's disturb our equilibrium by adding particles to our reactant side. It doesn't matter if I increase the H2 or I2 because they are both reactants, so I'm just going to increase one of them. By increasing the amount of H2, I now have the opportunity to create more successful collisions with I2. Since there are more possible collisions that can occur, we have an increase in our forward rate. When we increase our forward rate, we're going to produce more HI. So, as I activate each of those collisions, I've temporarily increased my forward rate. So, in order to reestablish equilibrium, I have to shift towards the right. We can expect a decrease in my reactants since I'm shifting the reaction towards the right, and we can expect an increase in my products. So let's watch this happen. We've reestablished equilibrium, and we see from the red marker that noted our initial position, we've increased our products and we've decreased the amount of reactants that we originally had. Notice that equilibrium does not restore to the initial position for H2, but we did decrease some of the extra H2 that we had available to us by our initial stress. So if we add more product, we're going to increase the number of successful collisions on the product side, which results in an increased rate of the reverse reaction. Here, notice there's only HI. So we'll watch it reach equilibrium. And here we are. Now we're at a same rate again. If I want to disturb my equilibrium, I'm going to add products, increase my concentration of products of HI. By adding more HI to my system, I'll create more successful collisions for my reverse reaction. This will increase the rate of my reverse reaction, and I have to shift towards the left side to create more H2 and I2. So we can expect a decrease in HI as this occurs because I'm shifting away and using up some of my HI. And as you saw, we had an increase in H2 and I2. All right. Now, what happens if we remove particles when we are at equilibrium? So to summarize, when we add products or add reactants, we shift away from our equilibrium position in order to use up what was added. If we remove reactants or remove products at equilibrium, we have to shift to replace what was lost. So here we are at equilibrium. If I want to shift this equilibrium towards the left, I need to remove some of my reactants. By removing reactants, I have fewer successful collisions. And that temporarily decreases my rate of my forward reaction. So if my rate of my forward reaction is decreased, then I will shift towards the left since my rate of my reverse reaction is higher. You can expect that HCl will decrease and Cl2 and H2 will increase to replace what was lost. Now we are back at equilibrium. So removing, again, shifts towards the side where we removed the particles so we can replace what was lost. If we were to remove something from the product side, we would see the same effect. It would shift to replace the products we removed. So let's go ahead and check that out. We're back at equilibrium. If I want to remove products, there are fewer collisions on the product side, which means I've decreased the rate of my reverse reaction. Less of these are colliding. So we'll shift to the right to replace what was lost. We'll have an increase in HCl and a decrease in H2 and I2. So in summary, increasing the concentration on one side causes a shift away from that side. Removing reactant or product results in a shift towards the side where particles were removed. So that way we can replace what was lost. When we are talking temperature, there are two types of reactions that we're going to look at. There are exothermic reaction, where heat is being released by the system, which is our chemical reaction. In an endothermic reaction, heat is being absorbed by the system, again, our chemical reaction. So since heat is being released in an exothermic reaction, we can view it as a product. If heat is going into the system, it's being absorbed by the system, we can view it as a reactant. So what happens when we start changing heat? Well, changing heat is the same thing as changing temperature. If we review kinetic molecular theory, we know a change in temperature is the same thing as changing the average kinetic energy of our particles. If we change the average kinetic energy of our particles, we're going to affect the number of successful collisions and therefore change the rate of either the forward or reverse reaction, depending on where heat is at. So removing heat will cause fewer successful collisions on the side where there's heat, and there will be a shift towards the side with heat to generate more collisions and more heat. Just like we did with our concentrations. If we remove something from that side, we shift back towards that side to replace it. If we add heat, we're increasing the average kinetic energy of our particles. We have more successful collisions, and we result in a shift away from the side with that heat. So again, if I increased heat on my reactant side, then that's going to cause more collisions with reactants, which will form more products. So we'll shift to the right. If I have heat as a product, that will cause more collisions with my products, which will shift to the left to create more reactants. I can show this on the simulation. Check it out. If you're playing this game at any point in time, level 8 can show this action of heating up and cooling down. Here, heat is going to be viewed as a product. So again, it's a product in the forward reaction, but it's a reactant in the reverse reaction. So if I want to shift my equilibrium to the right, that means I must remove heat to shift to the right because I want to replace what is lost. So by removing heat, I've slowed down my particles. I have fewer successful collisions on the product side. And that means I have decreased my forward reaction. So I must shift to the right and favor the forward reaction to replace what was lost. We should see an increase in my Cu and Cl concentrations. If I am trying to shift towards the left, I need to add more heat. Adding heat will cause more successful collisions between Cu plus and Cl minus. This increases the reverse reaction rate, and it will create more CuCl solid. Okay. The last level we're going to look at has to deal with pressure. If you're playing this game at any point in time, that is level 11. We're going to look at the effects of pressure changing. As I mentioned earlier, this is going to be related to kinetic molecular theory. Changes in pressure can only affect gaseous systems. When we increase our pressure, we have to think about the relationship that has with our container. This is basically an application of Boyle's law. We know that if the number of molecules stays the same and that the temperature stays the same, then there's an inverse relationship with pressure and volume. An increase in pressure results in a decrease in volume of our container. If there's a decrease in volume, there will be an increase in number of collisions with the walls of our container, thus increasing our pressure. If there's an increase in collisions, that means the side of the reaction that has more moles of gas will have more collisions, and therefore the rate of that reaction will increase. Here, I've got 4 total moles of gas, 1 mole of N2 and 3 moles of H2. Here I've got 2 moles of NH3 on the product side. If I increase the pressure on this system, there will be more collisions with reactants and therefore a shift to the right. Since there are more collisions with reactants, I'm going to form more products as a result. The forward reaction will be favored in this scenario. If I decrease my pressure, that's the same thing as increasing my volume. By increasing my volume, I will have fewer collisions with my NH3 particles. If there are fewer collisions with my NH3 particles, then I'll shift to the left to make more particles, since there's now more space for those particles to exist. Let's show that with our simulation. Here's our pressure meter. Remember, pressure is a measurement of the force of particles colliding against walls, not with each other. If we want to shift this to the right, I see there's 2 moles on the left side, 3 moles on the right side. So in order to shift with the side to the right, which has more molecules, I need to decrease my pressure. By decreasing that pressure, you'll see an increase in the volume. Since there's a decrease in pressure, there are fewer possible collisions. There's more empty space, less chance that they'll collide, and the reverse reaction requires more particles to collide. So there are now fewer of those collisions. Here we go. Since there's fewer collisions in the reverse reaction, we will shift. We now have more collisions with our forward reaction, and we'll shift to the right to increase our concentration of products. Something you might have noticed is the increase of products has also resulted in an increase in pressure. So we temporarily decrease pressure, and to restore that pressure, we needed to shift to make more molecules. More molecules can have more collisions, therefore higher pressure. If we were to shift to the left, on the right side of our equation is 3 moles, on the left side is 2 moles. Shifting to the left requires us to increase pressure, which decreases volume. By decreasing volume, I have more successful collisions with my product side, which means the reverse reaction increases in rate. If that increases in rate, we'll shift to the left to make more products or to make more reactants, and you'll see an increase of SO3. And since we have an increase in SO3, there are fewer particles of SO3 at equilibrium when this is finished, therefore the pressure should decrease. And if we notice our meter, the pressure is decreasing as we get back to equilibrium.